Well, hello there. Fancy meeting you here. This is Mr. Meyer from the lush studios of Way Happy, and we're going to talk about parametric equations. Now, they are fun. Now, you got to get a little used to them. You're going to be graphing again, just like you always have, but it's going to be a little different. In the past, we've done Cartesian or rectangular system, and that looked like this, right? Where you had one input, your input was x, and your output was y, and you plotted those points and everything was great. Well, in parametric land, you have also one input. It's called t now. That's your input, but you actually get two outputs. Now, what does that all mean? Crazy. Hold up. What's going on? So, in parametric, we can talk about usually an object uh, flying through the air. And we can give you the location. It's horizontal as it flies through the air. I can give you at any given time, I can tell you what the x value is and what the y value is of that object. And then that would change a second later. Say I could give you a new location of that ball or whatever it is flying through the air. So that's why there's two different equations, one for the horizontal and one for the vertical. And it's really kind of cool. You have what's your t values called your parameter, usually refers to as time, and you'll usually see these weird I things attached to them sometimes, and that's just telling you what your interval is, kind of restricting your domain of your input, saying, hey, make your inputs go, from this range to this range, this minimum to that one. It could be everything, all reals like always, or it could just be a little chunk, so we do it. And these can be really quite a blast. So let me give you an example of this first one. There's two parametric equations, the x equals and the y equals, and there's our interval time. And so in worst case scenario, if I were to graph this, I would do, all right, they want me to go from the times of -1 all the way to 3. I will give you what the x value and what the y value are. And then we could just plot it, right? And so here's what I would do. Let's plug in -1. We'd get 1 minus 1 is 0. And we'd plug it into the y value, and we get -1 plus 2 is 1. And so 0, 1 would be on our graph. And then we plug in 0, we get -1 for the x. And we plug in 0, we get 2 for the y. So -1, 2 is on our graph. Then I'd plug in a 1 and I would get 0 and 3 is on our graph, so I would plot that. And then I'd plug in 2, I'd get 3 and 4, and that's on our graph. Whoa, 1, 2, 3, comma 4. And as you can see, this thing is kind of building its way. It's going this way. And here I'll put little arrows showing you which way it's going. And then last but not least, I put in a 3, that's 8, comma 5. So is that 4 or 3? 1, 2, 3, 4, 5, 6, 7, 8, comma 5. 1, 2, 3, 4, 5 would be up a little higher. It's like here. And you can see that that is the path. And we would stop. We would go from one endpoint to the other, and you can see which way this object traveled, whatever it is, a UFO or whatever. And that's our equation. Now the cool thing too, you got to learn how to graph these on your calculator because it's just really neat. So you're going to take your calculator up. I'll give you a second to find it, or pause the video and grab it. And then the first thing you want to do is hit your mode button. And you'll notice down here that if I go down about 4, we are in function notation. We're going to move over one and do parametric notation. So that'll be the first thing I'm going to do. Now watch what happens when I hit the y equals button. No more y equals. What? You have an x and a y equation. So for the x equation, I would just type in what I have, t squared minus 1. Now you might panic, oh, I don't know where the t is. Well, now when you hit this x button that you usually use your variable, it is now a t button because it knows you're in parametrics. So t squared minus 1. And then you're going to go down and your y equation, you're going to write t plus 2. And now before I graph, I would probably like to hit my window button, and you can kind of control your window here. Now the T min, T max, that's your I values right there. So I want my I values, I want my time to go from -1 all the way to 3. And the step, who cares? Pick a small step so it graphs a lot of points. That's great. That's just how often do you want it to plot a point. Every 0.13 seconds I want you to plot a point. So that's great. I'll change it to 0.1. What do we need our x minimum from? Well, it looks like our x-axis went from -1 to 8. So just so we can see it, I'll go to -2 to 10. And our y's look like they go from about 1 to 4 or 5. So let's go from 0, or I always have to like to have a negative for some reason. I'll go -1 to 6. And look at this graph. What? Exactly what we did. So that is just too much fun. It just plotted the points and showed us exactly what we wanted to see. Neat, neat stuff. Now, as you can see, that graph that we just graphed kind of looks like a shooting star graph or a parabola or something. Sometimes people like to eliminate the variable t because they want to know what the equation looked like. So it's not a big deal. Usually all I'm going to do is solve one equation for t and then substitute it into the other equation. So pick whichever one you want. Maybe I would make this y equation, I would solve it for t, and I'd have y plus 1 equals t. And now I can substitute that into there, and we now have an equation. X equals 2y plus 1 plus 1. And if I make this look a little prettier, x equals, let me change that. I would subtract the 1 because I'd want y by himself. X minus 1 equals 2 times y plus 1. Then I would divide by 2, and this is going to get nasty because I'm going to run out of room. So I would have x minus 1 over 2 equals y plus 1. And now I would just subtract 1. X minus 1 over 2 plus 1, or actually minus, it's a good night, equals y. And there is what that equation would look like. I guess that looks really confusing. So what does that really look like? That's like 1/2 of an x minus a half minus a 1. So 1/2 of an x minus 1.5, so 3 over 2. That's what it looks like. Oh, this parametric equation, which I didn't know what it was before, I could now kind of tell you that it's going to look like a line that has a slope of a half and a y-intercept of -3 over 2. If you were just curious what it looked like. So if somebody wanted to know what it looked like, you could now tell them. Right? Look at the second one that I have right there. Same kind of thing. I don't know what this parametric equation would look like, so let's make one of them say y equals it, or t equals. It would probably be easier to say this, y over 3 equals t. Then I'll come cruising over here and have x equals y over 3 squared minus 2. And now I would go ahead and square that. So I have x equals y squared over 9 minus 2. I would probably move the 2 over. So x plus 2 equals y squared over 9. Multiply by 9 real quick. Y squared is equal to 9x plus 18. And if you know what that is, that's a y squared graph. That's a parabola opening in the y direction. We could square root it and get a plus or minus square root, and then you'd have the positive shooting star and the negative shooting star kind of thing. And so you'd see something like that. Again, it's shifted off of the origin, but it would look something like that. And that gives me an idea of what this graph would look like. So at the time, I didn't know what anything this graph would look like. But now, just a quick little substitution, and I do. Now, sometimes these can get tricky if somebody involves trig and you want to know what it is. So your x equation is that and your y equation is that. That could be a little scary because now it's hard to get t by himself. So like say you want to do it to the x, you would be like, oh, if I wanted to get the x by himself, then what the heck would I do? I would divide by 2 and then arc cosine both sides, and that wouldn't be very fun. And I don't want to substitute that in. That looks scary. So probably a better way to go about this is to find some other tricks. And one of the tricks that stick in the back of your mind whenever you're thinking trig is if you see cosines and sines, if they were squared, you could then maybe get rid of them. And that's the trick that's usually used on this. So I could say something like x squared plus y squared equals, now let me figure out what that is, 2 cosine t, that would be squared, plus 2 sine t, that would be squared. And what would that turn into? That looks like 4 cosine squared plus 4 sine squared. And I could factor out that 4 and have just cosine squared plus sine squared. And lo and behold, that's just 1. So that would equal 4. And I'd have x squared plus y squared equals 4. And so that's kind of a fancy way of seeing what kind of graph it is. Apparently it's just a circle with a radius of 2. And so you could enjoy that if you like. How about taking a line and turning it into a parametric equation or a line segment? This is not found in the book, but it's a little equation which I think they derive later on in the book, but they don't show it, is if I give you 2 points, then all you have to do is you can make a set of parametric equations that represent those 2 points, and then just give me the time interval. And if you have a line segment, then just restrict your interval from 0 to 1. If it's a line that goes on forever, then have your time interval go on forever, and you should be good. So what do I mean by that? Well, here it is. Here's your equation, right? And so if you want to make this into a parametric equation, there's a little line segment that goes from there to there. If you want to make this into a set of parametric equations, all I would do is say, all right, the x equation is going to be y1. Doesn't matter which one I call y1, but I guess I'll call, or x1. I'll call this the 1s and this the 2s for the sake of being in order. And I will have negative 4 plus, now notice I got to subtract them, so 3 minus a negative 4, that's 7t. And for the y equation, I would have 5, and then plus, now subtract them, negative 7t. And that would create a line segment. That equation right there is good enough to create a line segment in parametric equations that go from negative 4, 5 to 3, 2. I just got to tell you, only use the interval 0 to 1 because of the fact that I did a segment in this problem and not an entire line. And if you want, grab a graphing calculator and type that in, and you can see if you just do your step, your t step, if you go 0 to 1, you will get that little line segment from one point to the other. All right, that was a lot. Let's take a break, answer a question, and then we'll come back and do probably one of the coolest things ever, projectile motion. All right, nice work, but let's get to what we really want to talk about, projectile motion. So the fun stuff. You remember back in like chapter 2, I don't know, I think something or somewhere around there, we had a function, an equation of height of an object that you had, and it was the height at a given time is equal to gravity times time squared if it was in feet, plus the initial height of the object, plus the velocity that they threw the object in, the initial velocity, plus the initial height of the object. And not much has changed here. As you see, when I talk about parametric equations, if we just want to talk about something shot straight up, the height of the object, we kind of use those same equations. We just make x our time, and we can kind of follow the path of the thing that's been thrown straight up. Now, if you want to change that around and you want to know something more valuable, like where is that ball actually going after someone threw it and it's flying, we kind of add vectors in. Vectors always had magnitude and cosine for the x direction, but then for the y direction they would always have magnitude and direction. Now time, they will do that each second, they will travel that fast, and the x1, that horizontal, it'll just keep traveling horizontally, while the y vector, it will be going up at a certain angle, but then what will happen is over time gravity will start to pull it back down to earth, and eventually it should hit the ground. And so that's what's so neat about these two equations. Really look at these two equations and try to make sense of them, because what they are saying here is this is the horizontal distance that the object will travel, and the y one will be the vertical distance that it travels. And notice it will go up and then it will slowly come back down, and it all based on the velocity that somebody threw something and then how long it's in the air. So time and velocity are very crucial to these problems. So if you see my example there, Musa gets up to bat, hits a baseball 3 feet above the ground with an initial speed of 150 feet per second at an angle of 90 degrees. Will the ball clear the 20-foot fence 400 feet away? right? So, wow, what a great question. It makes me wonder, and I'm so excited. So quick, I will notice it's a projectile problem. So I will put in my projectile equations, which are the x, the horizontal distance it travels, is 150 feet per second, cosine of the angle, and that was 19 degrees. And now the only thing is, that was our vector equation, right? That was to get the initial horizontal component of the vector, the x component of the vector. Well, it's going to keep doing that every second it's in the air, so that's why we multiply this by t. This gets multiplied by t. Now, some people put the t in front, some people put the t in the back. You notice when I wrote the equation, I put the t in between 150 and cosine. As long as it's not with the 19 degrees, it's good, because that cosine is a function and we don't want it to be inside there. So make sure you don't. So it does. I don't really care how you write it, and you'll probably see that I try to write it mostly like this, just to get myself to make sure I don't accidentally put the t after the word inside with the cosine with the 19 degrees. That will tell us every second how far the ball has traveled horizontally. Now, what about vertically, the height of the ball? Well, same thing. You want to find the height, just do the height component of the vector would be 150 sine 19 degrees. That's what the height component would be, the initial height. It's going to keep doing that every second. But now the fun thing about projectiles is they have gravity involved. So you subtract off 16 every second squared. So every second squared, you're going to subtract off 16 feet. And you're going to start off with the initial height, which just happens to be ours, happens to be 3. And so now we have two beautiful parametric equations. Here is our x equation. And if you want, I can write this one the same way. 150t sine 19 minus gravity plus the initial height. That's the height of the ball that is going to be hit. And now I could grab a calculator, and I've already done it. I kind of snuck ahead and I typed it in, and you can see I got this beautiful equations typed in. So once I got them typed in, make sure you're in parametrics mode. Ooh, notice we're in 19 degrees, so I might want to make sure that my calculator is in degrees and not radians, because that would be a mess. And I want to check my window. The time I was assuming would go from 0 to about 3 seconds. I think it's going to be in the air for. You would guess this number right now, maybe. And then tell it how far you want it to go. I know I'm checking to see if the ball went 400 feet, so in the x direction, I wanted to make sure I included 400 feet, so I went to 430. And then in the y direction, I didn't know how high the ball was going to go, I guess 50 feet up, but I'm not sure. And then I hit graph, and you will see the path of the ball. What a shot, right? You can see that shot has reached almost the 400 and I think 20 or 30 feet that I've made. So you could trace it, you could do all other cool stuff that you want to see where the ball is at a given time. But it's not answering the question of 20 feet. How high is it when it's 400 feet away? So there's a couple of ways you could do that. You could go ahead and find out when x is 400, so this equation, when this equation equals 400, what's the time? And then I could plug the time in and figure out how high the ball is. Or, since we have calculators, we could just do this, right? Right here, we could say, hey, let's do another equation let's draw as the wall in. And what that would be is we make the x 400 because we want to travel 400 units out. So I will go out 400 units. And the y value, the height of the ball, that fence is 20 feet high. Now, how are we going to do that when time keeps changing? I can't just put 20 because it's just going to put a dot there, and that would be no good. But I could have it draw the fence if I say, hey, do t over 3, because remember we set our time to 3. So when t is 0, it'll draw 0, and then it'll keep plotting points all the way until t is 3, which will get us to 20. So now what I do is I graph it, and there it is, right? There is the height of the fence, 20 feet. And I can see that, bummer, Musa, it just hit the top of the wall. So you got a double, maybe a triple with your speed, and you're now looking good and about to score. Parametric equations, way too much fun, and I could just do these all day with golf balls or with basketballs or anything. We can see if we can see if the ball's going to go in, or a missile flying around if it's going to hit the target, or I mean, so many fun things about anything flying through, but you really got to get the equations down. You got to remember that your x is velocity times time times the cosine, and the y is the sine of that exact same thing, but it's got this gravity and an initial height. And each one tells a different story. X tells you how far it traveled horizontally, while y tells you how far it traveled vertically. Now, that's a lot of info, and they're definitely my favorites. I'm just going to skim over the last thing here. Circular motion. 2 more parametric equations. We can use parametric equations also to do circular motion, and so it's always fun to do like a Ferris wheel problem. And here are your 2 equations for your Ferris wheel type problems. Center is HK, the radius is R. B will have to be used with your period. Like, you remember in the old days, and still to this day, 2 pi over B is your period. So you will have to find out what the period it takes to repeat this cycle, and you'll figure out what B is, and you'll plug that in. What else would you have to know? I think that is it. Oh, so look at that. That's going to be in radians now, so that will be kind of important. So if I look at this example and I just set it up, and you can type it in your calculator and look at it, and mess with your window until you're happy. The radius of it is 30, so that's kind of simple. So I know I'm like x equals, well, let me draw a little picture here. It's 10 feet off the ground, and then here's the Ferris wheel, and we know it has a radius of 30. So that means that this thing right here must be, the middle must be 40 up, and then the top would be 70. Oh my gosh. So a little picture there helps me kind of figure out what's going on. So the center of my Ferris wheel would be 0, 40. So when I make my equations, I would have 0 plus the radius we said is 30 cosine. Oh, we got to figure out what B is. Well, they say that the period makes 1 revolution every 10 seconds, so the period is 10. So now I just got to figure out what the heck B is. Well, cross multiply and you get 2 pi over 10 equals B. So B must be pi over 5. And that's times time. And there's our x equation. Our y equation will be 40 plus the 30, because remember that was the center, plus the 30 is the radius, sine that exact same value, pi over 5t. And those are our 2 equations for now, this circle. And it cut me off before I could finish it, saying you went too long, but I got to at least show you the calculator because I thought maybe that would make somebody crazy. And so I got my 2 equations and I typed them in. And so I have the 30 cosine for the x and the 40 plus 30 sine for the y. I'm going to hit my window. Now t, that's again time. We know it takes 10 seconds, so I'll go from 0 to 10. The step really doesn't matter. That's just how crazy you want it to graph. The x's, look at our x's minimum. They got to go from negative 30 to 30 at least, I would think, because that's how wide the Ferris wheel is. And in the scale, I could care less. You know, that's a tick mark every 5 units. In the y direction, I'm going to have to go, I guess I like to see the ground again, so I'm going to put -1. But look at that, that's all the way up over 70, so I guess we'll go all the way up to 70. And again, the scale you could make is by tens or something. And lastly, the mode better be radians this time, not degrees. And if I hit graph, it should show me a Ferris wheel. Now, that's a pretty ugly Ferris wheel, but you get the idea. It did graph a beautiful circle Ferris wheel. It looks more like an ellipse, and that's just because my window is not proportional. So if that's really driving you crazy, you hit the zoom and you hit the square, z square, number 5, and it'll try to make it a little more squared window for you. And look at that. It is a gorgeous Ferris wheel, exactly what we thought. And we could trace it and find out where we are at any time, or we could plug in a value at time and I could tell you where you are on the Ferris wheel, and just super fun. So have a great day, stay happy, and we get to play with these for the next day, and I'll see you tomorrow.